And now we have a wonderful next talk from a very famous participant here, Professor Andre Geim, who got the Nobel Prize in Physics in 2010. And it's a great honor to have him here, and he's going to tell us today about proton transport through 2D crystals. Andre.
I have a clicker. Okay, right.
Andre, I think you might have to stick by the microphone.
Oh,
you've got that. It's all right.
You can stand on this side, and this is the camera that they'll see.
Sorry, I need to look there. Where should I point the laser? Okay. Right, okay. Thanks for inviting me. It's a pleasure to be here. I wondered what to talk about, but before asking what should I talk about, Tony put me in this energy materials session. I never considered myself to be a specialist either in energy or really in materials because I condensed matter physicist, but here we are. I decided to find out for this session something relevant. So it's proton transport through two-dimensional material, and this slide supposed to show, doesn't show much, show how, no, it...
The green button on the top, like this one.
What?
This one here.
Oh, yeah, I know that, but I like to use the pointer, and the pointer doesn't show up on the screen. Why? What? Oh, disappears. That's amazing pointer. So that's protons here. They run through two-dimensional material, and this is what I will be talking about, and this is people who will be involved, who were involved in this particular work, which we started about 5-6 years ago. My PhD students, then postdocs, and now they're professors, of course. So why should we be interested in energy material sessions about protons and two-dimensional materials? I don't want to discuss in detail, but generally there are every time you mention hydrogen and energy, it's a kind of system where you need a highly conductive for protons and impermeable for gaseous membranes. Fuel cells is one example, redox flow battery is another example, and actually at the basis of all those technologies is usually a very thin membrane or electrolyte, whatever you call it, which is proton exchange membranes, which allows proton go through and separate, say, between hydrogen and oxygen. Otherwise, if there is no separation, you know what's happened, it would be an explosion. So you have to be careful what to do. So gases should be impermeable and highly permeable for protons, because if it's badly permeable for protons, you get an extra losses, and say instead of 80% efficiency, you will have less efficiency. So it's a big business for 70 years. I think it's already started 70 years ago, and the current leader, I think it's so-called electrolyte, which is called Nafion, but there are many other examples of proton conductive membranes. So where two-dimensional materials come in, somewhere in 2014, we started with the following questions. Okay, so in theory and preliminary experiments at that time, it was known that graphene, ideal graphene, one of two-dimensional materials, should be impermeable for all gases and liquids. So A question I wanted to address is what about ions? And idea, for example, can lithium ions can somehow squeeze through and so on. So we developed, at that time it was quite a new technology, suspended two-dimensional membranes or silicon nitride membranes on silicon wafer and incorporate all this structure into kind of setup where you can put something from one side and detect what coming out through this membrane on another side. And this is how it's essentially look. It's at that time it was pretty small membranes, about several micron in size, and I don't want to show just a black hole here because I can say that something is there, but I want to show that it's indeed one atom thick membrane. So we burn here on the top contamination resistant. Now you see that it's indeed, there is something covering this hole. It's not the black hole, but there is a membrane here. So the first logically, maybe not in historic sequence, but kind of if gases don't go through, can we detect any ions going through? And it's kind of standard setup. You put this separator and put a couple of electrodes and measure what's going between those. And we measured here is shown 4 different solutions of salts, but we had probably 24 of those tested, and nothing goes through whatever we tried at all, so we can't detect any current going through, so ions don't go through. And then, to a big surprise, we have found that protons go through. This is HCl. Chlorine does go through, but you see immediately we observe quite a large current going through this membrane. So there is only one possibility to explain this, that protons go through this, and we can confirm it by many different ways. I don't want to go this, but it's kind of a nice experiment showing that only protons perfectly go through and all other ions rejected, measuring, okay, gradient of protons and gradient of protons according to Nernst relations gives quite a universal value. For gradient 10, it should be 58 millivolts at room temperature, so it's exactly like it is. So now we know that ions go through, but dealing with liquids in experiment, it's actually quite a hassle, breaking membranes and so on. So we looked for something more robust, employing what is typically used for decades already. So we take this proton conductive polymer, the same which is used in industry, Nafion, put a couple of platinum palladium electrodes. There should be proton coming in, interacting with electrons, and this is allowed all this current circuit to circulate. So now we add additional resistance. It's two-dimensional crystal to check out whether protons go through, and no surprise, protons go through. And we tried many different two-dimensional materials. In this case, at that time it was graphene, monolayer boron nitride, monolayer molybdenum disulfide, and found out that actually monolayer molybdenum disulfide, because despite its being rather defective, no protons go through, but the champion turned out to be not graphene in this case, but monolayer of boron nitride. Even bi and tri-layers show quite decent conductivity. And this is kind of qualitatively, you can understand that, because whatever you look at it in this building, it's actually all electrons, nucleus, this ball stick model. It's very confusing because those nucleus occupied a very tiny space. Everything else, it's electron clouds, and on the density of the electron clouds depends how transparent this atomic scale sieve is, and it's the biggest hole you get for boron nitride, slightly smaller holes you get for graphene sieve and molybdenum disulfide. It doesn't allow any protons through, at least with the best resolution we can get. So we also manage to measure activation dependence, and here came two surprises. One surprise that graphene showed for protons activation energy of the order of 1 electron volt. If this number would be 1.5 electron volts and we work at room temperature, we wouldn't be able to measure anything at all for those materials. So thanks to reasonably small activation energy, because its activation barrier to jump through those electron clouds, we were able to see something. And this contradicted very strongly to theory of, because according to theory, it should be about 2 electron volts. And people try to find why it is so little, and until recently there was a lot of disagreement why experiment disagrees with theory. Okay, some people even thought that our experiment is wrong, somehow we have holes, but okay, we'll hear about this a little bit later. The second is actually if you increase temperature to 200 centigrades, you get the magic number, which comes from the wish list of US Department of Energy. This is to the best possible material in order to work with all this hydrogen energy. So, and 200 centigrades is quite good temperature for operation of all those hydrogen energy storage and fuel cells facilities. So it looks promising, but we'll push further. So the next question was how really impermeable, what's supposed to be impermeable graphene. In theory tells us absolutely impermeable for gases and liquids, and we agree kind of that, but theory also suggested that it should be impermeable for protons. But we saw that protons can go through, so if you can't trust theory about protons, you should be checking carefully about other substances as well. In experiments, there was an experiment before us in 2008 by Yale group of Paul McEwen, and in the experiment it was claimed that it's absolutely impermeable, but in fact the nanoballoons they make, they deflate it within a few minutes. How those experiments work, essentially the idea how to measure permeability with respect to gases, you expose a container with trapped air to some permeable gas, and it goes through, and the membrane, because of an additional pressure, rises, and you can detect those small movements by atomic force microscope, for example, and that's the idea. In this 2008 experiment, they used silicon oxide, and silicon oxide was itself permeable to gases, and this is why nanoballoons inflate it and deflate it as long as you put it in some permeable gas. So, and accuracy, because the container is so small, a small amount of atoms coming inside, it can considerably change the position of the membrane pressure inside, and the accuracy is about 1,000,000 times higher than what you can get from a leak detector, the best helium leak detector, but it's still limited accuracy of these experiments. We decided a year ago, we decided to do something better. In this case, we used instead of silicon oxide, we etched graphite and boron nitride to make those very small micron-sized wells and cover them with graphene. You can probably see here that there is a kind of a material which goes above this cell. What is important in this experiment is that these sites are impermeable, especially for graphite. It's completely impermeable, and this is perfectly sealed because it's atomically attaching to the top surface. So if we expose this to helium, which is smallest and most permeable inert atom you can imagine, then, and wait for a month, we can reach accuracy that less than 1 helium atom per hour goes through those containers. It's 1 billion times higher accuracy than was achieved before, which is already 1 million times higher accuracy, which with respect to mass spectrometers, helium leak detectors. So what we know from experiments that monolayer is less permeable with respect to helium than 1 kilometer thick quartz slab. So if you take this billion times, the previous experiment shows that monolayer is less permeable than 1 micron thick slab of quartz. So quite a big step, and this current limit what we know about impermeability graphene. Then came other surprises. Okay, of course, being professional, you test many different gases, how they go through. Nothing goes through. Actually, we can punch those membranes and make an atomic scale, approximately 2-3 angstroms in size holes, a single hole, and you can easily detect flow of gases through this hole. But if there is no such angstrom scale hole in membrane, you can't detect anything. And it looks kind of what you expect, and what you expect from theory, but then we try hydrogen. And this is membrane. It's a little bended inwards because of interaction with the walls. This is typical position. It goes inside, but you expose, say, for 3 days to hydrogen, and you see it bulges out. So obviously hydrogen goes through. You can quantify it, all this stuff and so on. It's quite considerable leak, not enough to detect this with a leak detector, but using our technique, we can easily see that hydrogen goes through. And this is kind of very counterintuitive because it's a molecule and it's much larger than helium. And hydrogen is interacting molecule, not like inert gas helium. So that's one surprise. Another surprise came when we tried the same but using boron nitride, monolayer boron nitride. And we see monolayer boron nitride not permeable to anything, including hydrogen. So how does it happen? So the current thinking is well, we're practically sure what's going on. Graphite is the most inert material. This is everything more inert than PTFE or something like that. But graphene, because it's not flat, it's essentially a catalytic material as well. So we pretty sure that molecular hydrogen can be split at room temperature into atomic hydrogen at the surface of graphene. It has to be bended surface of graphene, not a flat surface of graphite. And then after this catalytic reaction, okay, the hydrogen atom goes through graphene, as previously I have shown you about proton reaction, because it's essentially tunneling of the proton. But we still go on. with this research. It has to be iron out details of this one. Obviously, we looked in previous slides at graphene, boron nitride, molybdenum disulfide, and this kind of materials were two-dimensional materials were reported already in 2005, that there are not only graphene but many sisters and cousins, and by now we know probably probably 1,000 different materials, few hundred of those were tried and investigated. So obviously there are other two-dimensional materials which should be more proton conductive, and it's one of our current research direction, try to find something better with more unusual, more proton conductive properties. One example, I'll give you two, is amorphous graphene. It's poorly conductive material because the structure of graphene is destroyed. You get not only hexagons but pentagons, heptagons, and etc., which kind of loosens up the crystal lattice, make those electron clouds which stop protons from permeating not so dense. And in this case, we also confirm that this material is impermeable to all gases and liquids except for hydrogen. Also, hydrogen leaks much less through this material. And for this material, proton conductivity 1,000 times better than for graphene and even exceeds the one for boron nitride. Unfortunately, not easy to make this material. What is promising is kind of mica materials, aluminous silicates. These materials has a tubular atomic structure in a single layer. This, each tube is actually blocked by ions, big ions, which are in plane, magnesium, okay, what other ions, but what is possible is to remove those big ions which are blocking those channels in the process, which is called ion exchange. Essentially, instead of those ions, you put it in any acid, and those ions washed out, and you get protons in those positions what you want to have there. And in this case, if you have non-ion exchange mica, you don't see any proton conductance, but after ion exchange, it becomes pretty proton conductive material. And previously I mentioned this magic number, which is desirable by industry, and this number is achieved at 200 centigrades quite easily, even not for monolayer. In this case, it's bilayer material. So the point is, how do we make these materials on scale? That's another question, but they satisfy, at least in an academic lab, they satisfy requirements of what is desirable for the industry. So what we learn, that from this, we kind of atomic lattice can be a sieve for subatomic particles. And this is kind of unexpected because, as I say, theory didn't expect anything like that, but it's happening partially because materials are not flat as theory often assumes. They have ripples, they have hills and valleys in those materials. So the question is, what else can we do with these materials? Because our lab dealing mostly with studying what materials can deliver, what interesting properties could be there. One of experiments which I think the most kind of fascinating which we have done, is take a vacuum chamber and cover this vacuum chamber by, that's the small obviously window, several microns across, but cover it with a two-dimensional crystal, say graphene, or boron nitride, and its vacuum withstand quite easily the pressure between vacuum and the room temperature. Then on this side we add proton conductive medium, naphion, and make a circuit which is proton injecting circuit. You need some hydrogen gas, a little bit hydrogen, and then we put current. So each time when electron comes here, its proton comes through here, through the blue part, and electron comes to graphene through this part. Together they make atomic hydrogen. And this atomic hydrogen goes into vacuum. And we can detect it with the leak detector in the vacuum chamber. And what you can see here, each electron leads to the creation of hydrogen atoms there. So it's kind of 100% efficient electrochemical pump, and you really don't really need much hydrogen outside. In principle, you can pump hydrogen even from air, from ambient air into the system. So of course it requires certain amount energy, and this certain amount energy is limited by resistivity of graphene. You can also improve this technique by adding catalytic particles, and actually by shining light you have an increase in performance by a factor of 100, and surprisingly 1 photon which goes onto graphene stimulates 10 to the 4 protons going through the membrane. We are still not certain. We speculated, of course, how it could be in our publications, but we are not certain how this mechanism essentially works. Further work has to be done. What else can you do? When you are dealing with hydrogen, and obviously the immediate question, okay, what happens with other hydrogen isotope, for example, with deuterium? And you can do the same kind of technology, but instead of water, you have heavy water, and naphion works with heavy water as well, and in this case you get deuterons going through. And we study all those materials before, how they allow deuterons go through. In principle, deuteron has the same size, subatomic size, the same charge. You don't expect actually any difference if you are serious, and if you say, okay, let's calculate difference between those, there would be no difference. But we have seen a difference by a factor of very close to 10 at room temperature between protons and deuterons, and all materials which are tested, they showed us the same difference. So this difference, apparently, because it's the same factor of 10, it actually comes not from the membrane itself, it comes from the medium, and I'll explain it a little bit later. But before doing so, we have done the same experiment to make sure that we get this different separation. For example, let us see, we take 50-50 hydrogen and deuterium as an input gas and push electrons on the circuit, and as a result we get 90% or so of hydrogen and about 10-15% of HD mixture here. So that's again the same separation factor of 10, which is arguably maximum achievable in theory for at room temperature separation. The reason we explain this is because protons and deuterons have different initial energies. That's the barrier created by two-dimensional material, but initial incoming protons and deuterons, they are connected to oxygen bond, and this oxygen bond creates kind of a potential well, and depending on whether it's deuteron or proton, there are different quantum oscillations called zero-point oscillations, and this yields the difference in energy about 60 MeV for oxygen bond, which gives this separation factor. So that's kind of explanation we have found. My last 5 minutes is, or even less, okay, I'm fundamental scientist researcher, but it's always useful to ask a question, can we use this one? Because it's all done on very small membranes in the lab and so on, whether this technology is scalable in principle. We know already for this picture from 10 years ago that you can produce graphene in square kilometers if it's required. It's relatively poor quality graphene with a lot of cracks and defects and so on. This is what we were dealing, not on kilometer scale, but at least on inch scale in our laboratory. Several years ago, we created less perfect examples of what we have done in the previous accurate experiments, and as an example of scaling up, we took the production method of heavy water, how to separate hydrogen and deuterium. So heavy water is quite a big business. 1 million kilograms is used per year by various industries, and which corresponds to about, requires energy consumption, which corresponds to million of US households. It's not as big energy consumption as, for example, mining for bitcoins, but it's quite still considerable example. So this is different technologies. Those two marks are what is usually used in industry. So that's an energy consumption, that's a separation factor. What you would like to be in this corner, little energy consumption and large separation factor, because separation factor translates in the footprint, how big your plant should be, and this usually, the plants which produce in heavy water are as big as petroleum plants, so it's really big machinery. This is what our experiment, not on industrial scale, but at least, okay, few inches size, shows the performance of membrane, which is at room temperature, at slightly higher temperature of 60 centigrades, I believe, where we work, and this is where we project it from even smaller membranes, about several micron size for HBN, where we would be there. Whatever you use, even for the case of graphene, which we reached in the lab, we get 99% energy savings, and we reckon that using 30 meters squared of graphene, which can be put in a small room in a cupboard, we can make a production equal to entire heavy water plant in this case. Remains to be seen, remains to be scale, and a lot of interest from industry, from nuclear industry about tritium, because it's even better performance, 30% separation between hydrogen and tritium factor, so people working on this one. So my last slide is that essentially it's an old industry, and it's old science, nearly a century old, but two-dimensional materials are radically different from conventional proton exchange membranes. It seems to be interesting, and it's not really as often wishful thinking, because there is quite a few patents licensed from us, from different industries, and I'm aware about several small startup companies who are trying to push it through, improve performance of Nafion by incorporating graphene together with Nafion, make better membranes. And that's all. Thank you.
Thank Andre, and also for a great talk. So we have one question actually from the audience online. So I'd like to open with that one, if you don't mind. Shijina, research scholar at the National Institute of Technology in Calcutta, India, asks, I would like to know the effect of layer numbers of graphene in the proton removal efficiency.
Low numbers.
The layers, number of layers, and the efficiency.
We only use graphene when we have bilayer graphene. It's an exponential dependence. So, for example, if you have monolayer of boron nitride, activation energy is 0.3 for bilayer of graphite, because it's sequential process, it's a factor of 2 larger, it's 0.6 eV. So if monolayer is 1 eV barrier, 2 layers would be 2 eV barrier, and it's completely exponentially impossible to see any transfer through this system.
Okay, thanks. Oh, there's a question over here. Ram?
Yeah, thanks. Thanks for a great talk. I have a question about this idea that the hydrogen dissociates and then recombines on the other side as it permeates. Is there an electrical signature on the graphene? Have you ever considered just looking at the electrical properties of the monolayer graphene as you expose it to hydrogen?
It's a good question, okay. So we try to, these days devices are essentially encapsulated and they show very high quality. Intentionally, we did intentionally expose graphene to atomic hydrogen, and we do see reduction in mobility, it becomes worse conductive, and so on, to see whether hydrogen itself, just without molecular hydrogen, reduces mobility. It's kind of a difficult task, requires especially dedicated experiments, and we haven't done it. So it's because it depends on the number of attached atoms and so on. So it's not that easy, but in principle feasible.
Okay, I think we're going to have to leave it there.
Ben.
Go on.
Oh, sorry, Ben is asking a
Oh, sorry,
question,
go on.
okay.
Ben.
With
Go on then.
respect
Last
to
question,
Nobel
we-
Law.
Last question
Is
then
there
from
still
Ben here.
time for the question? I'm also intrigued by this hydrogen binding tunneling, you know. So you said the banding of the graphene locally, you know, enhances it. So how much banding is needed, you know? And if you would put a mechanical force on your membrane, would you enhance the transport?
Probably yes, but there are static ripples on graphene which are induced there. We know we see them in TM, which are nanometer scale. But in addition to that, there are plenty of dynamic ripples, which are just thermal vibrations of membrane. And this is because there are so many of those that would be, and actually the strain and curvature is quite remarkable, about reaching a couple of %, which is a really large strain. I don't think that with AFM tip or anything like that, you get the same effect as from many, many smaller ripples. So this experiment is in principle feasible, but would be difficult, but we have enough ripples in the system already.